Hi, welcome to OpenLC Solutions. Today we're going through the 2012 paper 1 and we're looking at question 6. Now this question is all about functions and calculus. So it gives us this diagram here which shows a graph of this function f, it's the curvy one, and it also has these two lines k and l, but they don't come in until a little bit later. It does tell us the function f is defined as x cubed minus x squared minus x plus 6. And we're asked to find the coordinates of the point where f cuts the y-axis. So what is this point here? Where does f cut the y-axis? Well, it looks to be about halfway between these two notches, 4 and an 8. So you expect the answer to be maybe 6 or so. But we can actually find it exactly because we know that every single point on the y-axis, regardless of whether it's an intersection point or it's just any other point on the y-axis you pick, any of those, they share something in common, and that is their x-coordinate is 0. So what this question is really asking is, if the x-coordinate is 0, what is the y-coordinate of the function f? So we can find that with this f of 0. We know that's x cubed minus x squared minus x plus 6, so that's 0 cubed minus 0 squared minus 0 plus 6, that's replacing all the x's with zeros, and so you get a 6. And that gives you the y-coordinate. It's asking for the coordinates, so it wants both of them in brackets, so you say the answer is 0, 6. It then tells us in part B that f has a minimum turning point at 1, 5, and we have to find the coordinates of the maximum turning point. So you might know turning points as stationary points either, but the point is that at a turning point, the graph just goes pretty much horizontal. And that happens in two places with this function f. It happens there. You can see that the graph is almost horizontal going through that point. And it also happens here. You can see the graph goes almost horizontal for a while and then it goes back down. It tells us that the minimum turning point is at 1, 5. So this point here, we already know is the minimum. So that other one must surely be the maximum. And you can tell whether something is a maximum or a minimum just by looking at it as well, because you know that maximums have a kind of N shape. They go up and then they go back down, whereas a minimum will have a kind of U shape where it goes down and then back up. But the main question here is, how do you actually find one of these turning points? And the answer to that is, you know that all turning points, because they're pretty much horizontal, they have a slope of 0. And so what you can do is you can set the first derivative of the function to 0, and you'll get an equation that you can solve. Well, what is the first derivative of this function f? Well, the x cubed becomes 3x squared when you differentiate. The minus x squared becomes minus 2x, and the minus x becomes a minus 1. So we now have a quadratic equation, and if we solve this, we'll hopefully get the x-coordinates of the turning points. So you get 0 equals, let's say we're going to have 3x, x, 1, and 1. We need this to be minus 1 to make the minus 3, and this has to be a plus 1. And so the answers are where the first item in this product is 0, so 3x plus 1 equals 0, in which case x has to be minus 1 over 3. And the alternative, case 2, where the second bracket in this product is 0, that's x minus 1 equals 0, in which case x equals 1. Now we already know that the second answer here is not what we're looking for. And how do we know that? We're told that the minimum turning point is at 1, 5. So we know that that already corresponds to the minimum, and we're being asked about the maximum. So this x is minus 1 over 3 must be the answer we're looking for. Now that's only the x-coordinate of this, but we're asked about both coordinates, so we need to figure out what is the y-coordinate, and we do that by putting that into the original function. So f of minus 1 over 3 becomes minus 1 over 3 cubed, because it was x cubed, then minus 1 over 3 gets squared because it was a minus x squared, minus 1 over 3, be careful of your signs, and then you have a plus 6 left over. So that becomes minus 1 over 27. The next bit is going to be minus 1 over 9 when you work out all the different signs. And we're going to have a plus 1 over 3 and a plus 6. And this becomes 167 over 27, or if you prefer mixed numbers, that's 6 and 5 over 27. So that's the y coordinate. We have to finalize our answer by writing both coordinates in a bracket. So we say minus 1 over 3 and 167 over 27. Part C brings in the two lines that were in the diagram in the first place, K and L. We're told they're tangents to the curve F, and we're told that L is parallel to K. The equation of K is given to us. We have to find the x-coordinate of the point at which L is tangent to the curve. So let me just go back to the diagram to show what it's talking about. It gives us this line K, gives us the equation for that. Tells us that L is parallel, so you can see kind of by looking at it that those two should be parallel. And it's asking for the x-coordinate of where L touches F. So the x-coordinate of this point here is what you're actually asked to find. How do we do that? Well, we know that K and L are parallel to each other. In other words, they have the same slope. We're given the equation of K, and so we can work out the slope from that. So if K is given by 4x minus y plus 9 equals 0, I'm going to rearrange that into the standard form of y equals 4x plus 9. And when it's in this form, when you have a single y equals something times x plus a constant, this is the slope. So the slope is 4, and since the slope of k is 4 and L is parallel to k, that implies that the slope of L is also 4. Now, how does that help us? Well, the slope of a function is given by its derivative. So we already know that f prime of x, the derivative of f with respect to x, is given by 3x squared minus 2x minus 1. We worked that out in part B. And we know that that is equal to 4 because that's the particular case that we want to know about, where we have this line L, we have the slope is 4. So when are the slope of those two things the same, which is what happens when you have a tangent. So if we solve this, we should be able to work out the x-coordinates where this is true. So we get 3x squared minus 2x minus 5 equals 0. And we can factorize this one. So we get 3x and x. How is this going to work? We're going to have a 5 there and a 1. We need a minus 5 and a plus 1 for this to work. So case 1, we have the first item in this product equals 0, in which case x is 5 over 3. Alternatively, we have the second item in the product, x plus 1, equals 0, in which case x has to be minus 1. So why are we getting two answers out of this? Well, let me just go back to the diagram and we can see there are two places on this graph f where the slope is 4. We already know one of them because that's the idea is we're meant to find this point. The other one is where k is a tangent to the graph, because k and L have to have the same slope. Since they're both tangents to the function, which we're told in part C, then there must be two places where the graph has that slope. Now we need to eliminate the one that's k, because we're specifically asked about where L is tangent to the graph. So k is more to the left than L. You can just tell that from the diagram. And so the larger number, the one that's further to the right on the number line, must be the x-coordinate of L. So which is that here? Well, we have 5 over 3 and minus 1. And minus 1 is the lower of the two numbers, so that surely must be where k is tangent. And the other one, x is 5 over 3, must be where L is tangent. So that's all we were asked to do. In this case, we weren't asked about both coordinates. All we need is the x coordinate of this point. So we don't need to put that back into the function and work out what the y coordinate is. That is the question finished. So thank you very much for watching, and hopefully I'll talk to you again in the next episode.